What's up? Today we'll be talking about the pressure and density question. I have a worksheet for you with basically the 4 equations you're going to need to know for the pressure and density question. We'll go through that in a second. I've also extracted all the questions from past papers from 2015 all the way up to 2023 now, or 2022 I guess. And then you've got all my written answers there for you as well. Okay, so pressure and density. First of all, we need to know what pressure and density are. So density is basically the measure of how tightly matter is packed together. So this obviously differs from material to material, but the formula for density is mass divided by volume. So if you want to calculate the density of something, you need to have its mass and its volume. Divide those two bad boys together, you get its density. And it's just a property. It's just something we're saying, okay, that's how dense it is. Mass divided by volume. Some important volumes, because we'll get different shapes, but the common shapes are a sphere and a cylinder, and that's the volumes of those. Pressure is just the measurement of how concentrated a force is. So this is force, the force acting on something, the force times the area it's acting across. So what would be a good example, like a high heel, the person may weigh the same, they'll be wearing different shoes. Let's say one person's on a high heel. Well, that high heel, because the area is so small, well, the pressure is going to be a lot on the ground. But there's going to be the same weight, right? If she was wearing like a slide, well, then there's a bigger surface area of the foot. Maybe that's a good way to think about it, so there'll be less pressure. But pressure is force divided by area, is the unit Pascal. And then you need to know these two things. It's called hydrostatic pressure and Archimedes' principle. It's these two equations here, and I'm actually going to prove them both for you right now, because it might look a bit weird, like where the hell does this come from? Basically, this equation here says the change in pressure equals the density times gravity times the change in height. This is basically telling you, or pressure equals density times gravity times height. This is telling you the pressure at any depth h within a fluid of density mu, or whatever, p, slanted p. That's what that's saying. So if you pick any point in a fluid, well, this will tell you what the pressure is at that point. Pretty helpful. And Archimedes' principle just tells you about the upthrust. So you might have felt when you go into some water, you feel like a force kind of pushing you up. That's why objects float. So this is giving you the upthrust, and this is due to the change in pressure. But Archimedes basically stated that an object submerged in fluids has an upthrust equal to the weight that is displaced by that object in the fluid. I'm actually going to go ahead and quickly prove these, because why not? We've got a bit of time. So we want to prove these two equations, because you might be like, well, where the hell do these come from? Change in P equals rho G, change in H. And the upthrust, F up, equals rho GV. Okay, so I'll just quickly prove these. So let's say if we had some container with some fluid in it. Let's say it's at a height h. Look at this drawing. I know you love it. Okay, so if we wanted to find, we'll say the bottom has a surface area A. So if we wanted to find what the pressure is at the bottom of this tank, let's say for example, well, the pressure at the bottom of this tank, that pressure equals force over area. And so what is the force acting on this bottom of this tank? Well, it will be the weight of all of this liquid, or the weight of this water, right? So this will be the weight of the water divided by surface area A. Right? And what is weight? Well, weight is mass times gravity over A. Right? And so the mass of the water times the gravity. Well, how would we find the mass of the water? I mean, we're trying to get this. So the mass of the water, well, we know that rho, or the density of the water, will equal to the mass of the water times the volume. Right? So therefore the mass of the water equals rho V. Right, we substitute this into here, we get therefore P equals to, well, the mass is this in terms of the density and the volume. It'll be density times volume times G over A. Right? And finally, well, the volume of this entire thing was just going to be the area times the height, right? It's going to be rho times the volume, well, the volume is the area times the height, G over A. And then the A's will cancel, and you get this rho G H. So the pressure at depth H is equal to this. And so therefore the change in P, so the change in pressure between 2 points, which is very useful because it helps us find the upthrust, is rho G change in H. So the difference between 2 points. So if you took, 1 point here at H1 and 1 point here at H2, well, the difference between these 2 points would just be, the change in P will equal to, the change in P will equal to rho G H2 minus H1. Also, at any depth, you can find the pressure. And that's hydrostatic pressure. So this is for a liquid that is at rest. It's equilibrium. Okay. And, why do we do that? Well, because, from this, we have this area. And so we have an equation that involves pressure, which has nothing to do with the area of, which is in contact with that point of pressure. It's quite an interesting thing. It's actually quite a useful equation, especially if you want to go into engineering. Not that I'm a fan of engineering. I appreciate it, but I'm not a fan. More of a theory guy. Okay, and then this one. So this is Archimedes' principle. It's actually quite easy to prove. Sorry for this being a little messy. Rho GV. Okay, so this is saying that, so let's say if we had another, let's say, very prepared here. Again, we have a liquid. Let's say we have some object in it. A cylinder like this. So this is some liquids with some object in it, which displaces some volume of water, right? When you get into a bath, the bath moves up. So it's completely submerged in water. Well, what we can say is this object experiences some upthrust, some force upwards. And what will that force upwards be? Well, because of it's submerged with water, we'll have some pressure. If we just look in the vertical direction, there's going to be some pressure, Fu, on the top. Let's say F on the from the water, right, on this object. It's going to be pushing on it, and also from the bottom. All right, there's going to be two F bottom, bot. Okay, so it's going to have pressure from a force from the top and a force from the bottom. So the net force on this object here, remember this, I'm also saying that it's at equilibrium. So it's at rest. It's not moving anywhere. So the net force on this object will be, F bottom minus F top. Right, they're acting in opposite directions. One acting down, one acting up. So the net force will be just the sum of these two things. And we know that F, the pressure, equals to force over area. Right, this thing has an area. So therefore, the force equals pressure times area. This would be the pressure at the bottom times the area minus the pressure at the top. I'm just substituting this into here. Times the area. Factor out an A, what's the pressure at the bottom minus pressure at the top? What is that? That's the change in P. Change in pressure. And that we found before. Equals to A times rho GH. Rho G change in H. This equals to rho G change in HA. And what is this? This is change in H times A. For this will just be the volume. Volume of the object or the volume of water displaced. This will be the volume. There, that's the upthrust. A little messy, but yeah, that's a proof for it. You don't, I guess you'd probably need to prove this. We'll just know where it comes from. Because I don't think they give it to you, but yeah. Another way to think about it, because Archimedes' principle is saying, the upthrust is equal to the displacement and the weight. So it's basically equal to the weight of this object. That's what it states. So that's mg, right? And we know that m, like from before, m equals pv. So this is another way to do it. So m is, pv. It's the same thing. Whoa. Real lazy with the handwriting today, huh? Okay, probably a bit too long, but look, there's two proofs for those two equations. And you should probably understand them, but let's jump into the questions now. So with those four equations, that's all you need to answer all the questions. And obviously you need to be a badass as well, but I thought that's a given because you're watching my channel. Okay, so we have some cylinder, disk of mass, this circular. Okay, so we've got some weird ass scenario. We've got some disk and it's moving along the ground. We have a force acting at some angle on the disk and it moves at a constant speed. Determine the rate of doing work. Well, what is the rate of doing work? Well, if you should have watched my force energy question video, the rate of doing work is power. And power, I got the power. And power is force and velocity, where force and velocity are acting in the same directions. Okay, so the force, so we need the component and the force acting in the same direction as the object is moving, or as the speed or velocity. Right, so we have some force here acting at some angle, 30 degrees. It's a force of 8.9 newtons. And, oh no. And so it has a vertical and horizontal component. And this force here that we're interested in, let's call it Fx, is this, right? The horizontal component is acting in the same direction as the velocity, or this disk is moving, right? So therefore, opposite adjacent, so, this whole steez is equal to adjacent Fx over 8.9, right? Cos equals adjacent over hypotenuse. Okay, so Fx is equal to, I feel like I go too fast. Fx is equal to 8.9 cos of 30 degrees. Right, so that's the force, the component of this force acting in the same direction as the speed or the velocity. That means this is going to be, the rate of doing work is going to be 8.9 cos of 30 degrees times the velocity is 0.6. And then you put that all in your calculator. 4.6 watts. 4.6 watts. So I'm always rounding to two significant figures. Like, this is a beast of a number, but I'm rounding to two significant figures. Okay, the force X and the weight of the disk combined. So this is pressure now. So, this X will also have a vertical component acting down, which will be pushing the disk down, but it also has the weight pushing the disk down onto the ground. And so with these two forces, there's going to be pressure created on the ground, sort of like what I was talking about before with the heel. Okay, and it's also going to be equal to, this pressure, like we just saw before, is force divided by area. So therefore area is equal to force divided by pressure. We have the pressure, which is experienced on the ground. But the force is going to be equal to, well, Fy now. Y will just be doing the same thing, but instead of cos, it will be sine of 30 degrees. So this thing here will be Fy plus W over P. So for the pressure, right? Because those are the two vertical components which are pushing the disk vertically down onto the ground and causing this 3,500 pascals of pressure. Okay, so this is going to equal to 8.9 sine 30 plus the weight, which is mg, mass mg, which is 0.24 times the gravity, is 9.81. So this thing divided by 3,500 So therefore, and again, they don't give me enough space. I'm about to go beat up the entire room full of exam writers. So you put all this into your calculator and you will get 1.94. 1.94 times 10 to the negative 3. So meters cubed, meters squared, sorry. Right, it's always important as well to check that things are in base SI units. You know, so this is in meters per second, this is in kilograms, so we're all good on that front. If not, then you have to, you know, change your quantity. Cool. Newton's third law. Okay. So one such pair, so that forces always act in pairs, and they're equal and opposite to each other. So it's saying we have one of these pairs of the weight of the disc. So we have this disc, it's got a weight and it's pushing on the ground, right? But then there's also going to be a normal contact force pushing up, which they're calling y. So the direction will be up. And name the body on which the force acts. So this is the Earth, right? Our beloved Earth. So x, so the Earth, this will be the Earth. Right? Equal and opposite. Go watch my video on force energy. Okay, let's do another one. So a cylinder is suspended from the end of a string. The cylinder is stationary in the water. Okay, so it's just cylinder. So it's just submerged in this water. Okay, so what do they give us? They say that we're given the weight, we have the height of the cylinder, the diameter of cylinder, the water, the density of the water, and it says that the change in pressure, so the difference in pressure between the top and the bottom, well, we can already see that we're probably going to be using this, right? Writing. Right, the change in pressure between the top and the bottom is 520. Scales. Calculate the height. Well, change in P equals rho G change in H, which I proved just before. So therefore, change in H equals to change in P over rho G. Okay, change in P is 520 divided by the density of the water, which is 1 times 10 to the 3. G is 9.81. 1 is 10 to the power of 3 times 9.81, 520 divided by answer 0.053. This gives us 0.053. So the change in height, so the you know, between here and here, which is this height, h, right? So the pressure here and here, the difference in pressure is 520. We calculate, well, what's the difference in height between those 2 points, and the difference in height between those 2 points is h. So this is 0.053 meters. And again, it's in meters because everything else is in SI base units, so we're chilling. Sometimes they put it in, you know, they might do centimeters or something like that, and you just have to catch that out and then just change. So show the up thrust acting on, okay, well, this is just, do this in a couple ways. Remember, our up thrust is just rho GV, right? So we could do it like this, find the volume of this, right? Volume of this displace, we have gravity, and then we have the density of water. So we could do that to find the up thrust, or we could say, you know, the up thrust equals to the change in P times area, like I showed in my proof, right? It's due to the difference in pressure, because, you know, force equals pressure times area. Right, let's do it this way because it's cooler. And we also have the change in P, which is helpful. So the change in P is 520. Change in pressure, and the area, well, it's just going to be the area of the space, right? Which will be pi, just a circle, so pi r squared. This is the diameter, so we need to half that. So r squared is going to be 0.031 divided by 2 squared. This should equal 0.39. And it will, I promise you. I'm a G. Times pi. Imagine if it didn't. It's so embarrassing. It does, look at that. Okay, so this is 0.39 newtons, rounded to 2 significant figures. Calculate the tension in the string. Okay, well, we have, is that it's stationary, right? If it was moving, we have this thing called viscous force. I think that's what they call it. Yeah, that is. But basically, it's a resistance force of the water. But it's not moving. So we only have this upthrust force due to the buoyancy. We also have the weight. So this F upthrust with the weight. And then we also have this tension in the string, just kind of pulled out. So the tension and the upthrust act up. So, and that should equal to the weight, right? So the up forces equal the down forces because it's at equilibrium when it's stationary when it's suspended in this water. Okay, so the tension will just simply be the weight minus the upthrust. We have the weight, 0.84. Sorry, 0.84 minus the upthrust, which is 0.39. Yes, I'm going to use my calculator, don't judge me. 0.45. Right, all I did is resolve the forces. I know it's at equilibrium, so the sum of all the forces in the vertical direction are going to be 0. Well, the up forces are going to equal to the down forces. Okay, so I calculate that. This comes up quite a bit. Summing forces. Forces are important in physics. And I feel like this video is getting too long. Let's go, go, go! Who's still here? The string is now used to move the cylinder vertically upwards through the water. Okay, so this is going to be kinematics, I'm pretty sure. And I already spotted centimeters. Okay, they're sneaky with this. They're sneaky with this. They're trying to catch you out. They're sneaky. So be checking the units. Okay, so determine the acceleration at 2 seconds. Okay, so 1, 2. So remember the acceleration is just going to be the gradient of this graph, or change in v over change in t. So at 2 seconds, it's going to be, and I remember that it's in centimeters, but it's going to be 2, and this is what? 7, 8, 8.5. So each of these things are 0.5. So this is going to be, change in v is 0 to 8, so 8 minus 0 divided by 2 minus 0. So this is 8 divided by 2, also known as 4, but it's 4 centimeters per second. So in meters, just be 4 divided by 100. Sorry, is it a brain? Right, 1 centimeter is 100 centimeters is a meter. So this is going to be 0.04 meters per second. Cool. The top face of the cylinder is at a depth of 0.32 meters below the surface of the water at time. Okay, so at this point, it's at this depth. But obviously it's being pulled up, so it's going to start moving. So use this to determine the depth of the water at 4 seconds. So we just need to find the displacement of this object, which is the area under this graph. Go watch my kinematics video. Okay, so we just find the area under this graph. It will give us it in centimeters. Change that into meters, and then just minus that from that to find the depth. So S equals 2. Well, this is a triangle. It's supposed to start half base, which is 2.5 times height, which is 10, plus this part here, right? I mean, you might think, well, then isn't this moving the opposite direction? No, just think about it. It's the velocity is still positive, so it's just speeding up here, it's accelerating, and then it's deaccelerating here. So it's moving faster and then it's deaccelerating, but it's still moving up. This is all positive displacement. Okay, so 2.5 to 4, this is 1.5 here. So the base 1.5 times the height, again, would be 10. Okay, and this will give us 25 divided by 2 plus 15 divided by 2, 7.5, so plus 7.5. It's 20. So this is, and remember it's in centimeters, so 20 centimeters or 0.2 meters. So therefore the depth will be, well, it starts at 0.32 and moves up this, so the depth will be, no, I'm not putting in my calculator, 0.12. So 0.12 meters. The cylinder is released from the string at 4 seconds and then it falls from rest vertically downwards in the water. Assume that the up thrust acting the cylinder remains constant. Name the force that acts on the cylinder when it's moving up. Okay, so when it's stationary, it doesn't have this frictional force between the water and the object called the viscous force. I'm pretty sure I'm pronouncing that right. This force here, this is basically the friction force. So when it's moving, it experiences a friction force along with the buoyancy. So this is important. So when an object's moving, usually in all the questions they're stationary, they use stationary objects, but when an object is moving, there is a frictional force, right? Obviously, because it's moving and it's experiencing friction between the body that's moving and the water. Just like when you're moving, you have friction between like some object and the floor. State and explain the variation of any of the acceleration of the cylinder as it falls downwards through the water. Well, as it falls downwards through the water, similar to like a skydiver, I mean, it's the same thing. It's just the skydiver is submerged in air. In this case, it's submerged in water. So when it's falling down the water, this force, this viscous, that's a weird word. Viscous force is gonna increase, right? And this is a force opposing the motion of the object. So if this is increasing as it falls down, right? Well, then the acceleration, the net acceleration downwards through the water is going to decrease. Right? It's going to slow down. It'd be weird if it sped up, right? Just you jumped in a pool and you just started accelerating. So the acceleration decreases as time passes. Cool. That might have been too long, but yeah, we did some questions. I did some proofs, but you have the theory here. You just need to know these equations. 1, 2, 3, 4. Maybe the proofs are clearer on this worksheet, but there, you just need to know those equations, where they come from, what they're about, their life story, and then you got the questions here, which you can go through. Now I'm going to talk about pressure and density from a philosophical perspective. Right, so what do we really learn from studying pressurized systems? What we really learn is that pressurized systems produce large amounts of energy. Steam and stuff like this create pressurized system, we can produce large amounts of energy. And really the idea is all embedded in this sort of topic which you've just been introduced to. These ideas really accelerated human life. I mean, this would be the cause of the Industrial Revolution, and it accelerated human life a lot. I mean, we started to produce a lot more, because we could use these pressurized systems to enhance our lives and, our survival. And really that's the power in physics and science, the scientific method, is that we use it to gain insight into the nature of reality, and then we sort of use that insight. So in this scenario, pressured systems, to enhance our own survival, evolve us, and basically elevate us to a point almost above nature itself. And I don't want to be cliche, but I mean, with great power comes great responsibility. And so, are we even ready for this power? I mean, are we psychologically mature enough for this power? Because I feel like we misuse it. It's almost like nature shows us these amazing properties and things that it has. And like I said in my previous video on torque, nature has an inherent property of balancing itself out. And if we sort of take these insights and then just use it for our own self-interest to gain for just humanity, we only think about ourselves. It's quite myopic, short-sighted. And I feel like there will be massive ramifications. If not, there's already ramifications for this. Treating the earth, let's say, just for an example, as just a place to harvest resources and use to elevate ourselves to higher levels, there will be consequences to this. The earth is not an unintelligent. If you think the earth is just some stupid rock, I mean, you're deeply mistaken. It will balance itself out, and if we push too far and we don't we get cocky almost, there will be ramifications for this. Now, this does worry me a little bit. I don't want to freak you out. And so You know, the scientific method has given us amazing insight into the world, into the universe, but are we using that power correctly? Are we mature enough to use it? I don't know. I'm not sure, but it seems like we don't really care. We only care about ourselves and pushing the agenda of humanity. See how that turns out, but like we should be a little more careful and a little more mature with the insights that we get, the knowledge that we obtain from science. I even think about that when I think about AI and where that's going. But anyway, I'll stop now. That's all from me. If you need A2 content, it's on Patreon. I will eventually do A2 physics as well after this, but that's it. Peace out.